Okay, if I can grab everyone's attention quickly, I know some of y'all are still answering the questions, that's okay. But I want to talk about a couple of things to help us get started. So we're going to look at the, really quickly, just so I don't forget. Miles, don't forget you're up on, where's Miles? Hero Friday tomorrow, right? Thanks, buddy. I need y'all to start thinking about who wants to volunteer for next week, but Miles has got us tomorrow. Today we are going to focus on linear versus exponential functions. So I'm going to ask a couple of questions in a second about that. And then today we're finishing up to use or not to use algebra, the dream job salary, and we'll get some practice with linear versus exponential. One thing I do want to point out or let y'all know is I looked through y'all's feedback on preparing for the test, and just a couple of things that I want to make sure are clear, because a couple, one of the most common things that people were asking for that I could do more to help you prepare for a test is practice questions. A couple of things with that to think about is, one, make sure you're doing all your check your understanding questions. If someone finishes all the check your understanding and wants more practice, I'll be more than happy to find some more. But on top of that, okay, is it okay for you to rework a problem? Yeah. Like, if you want to write that problem down on a separate sheet of paper and then rework it and check your work against what you've already done, that's actually a great way to study. So like, if you want more practice, that's what I would suggest, on top of looking at the practice problems we've done in class. Okay? Is that one of the old ones? So that's what I would recommend practice-wise. If you're saying, hey, I need more practice, I would do the check your understanding, and I would probably do them earlier. I think that's why some of us got a little behind, is because we didn't do the check your understanding when they were given, not assigned, but given, so that you could check your own understanding. That's where I would start. There's only so much time in a day, and so we can't do a ton of practice. I did see where someone has said, hey, to help me better prepare, I wish we had had 5-10 minutes to study in class before the test started. So I am going to go ahead and tell you I'm going to push back on that. That's not to help you better prepare, that's to help you cram before the test. What I want to do is help you better prepare, not so that you do better for 5 minutes on a test, but that you do better long term, okay? Which means, and so one of the things I absolutely hate about the block system is that we have hour-and-a-half blocks for a single semester, so you're basically cramming all of it into a single semester. What research has shown is that learning takes time, and not like cramming it in an hour and a half, but like over multiple days, right? Like, it takes time for ideas to set in. So instead of taking 5-10 minutes to study before the test starts, I would start earlier. Like, I would start about a week out when you know it's coming and just study a little bit. Not hours a day, but 15, 20, 25 minutes a day. Little bit at a time, making sure that you're driving it home. That's probably the most effective way to study. So the other thing I'll say is this. If you go to college, which having talked to most of you, it feels like most of us are planning to go to college, your teachers, your professors are never going to give you 5-10 minutes to study in class before you take a test. So we got to make sure we're doing that before we come into class. I know that's counter to what some teachers are doing, but again, that's not helping you be better prepared, that's helping you cram. And I don't want you to cram, I want you to learn and understand. There was something else that I saw, but I don't remember it off the top of my head, so I'll have to look back through. And again, if you want to push back on any of that, if you want to talk to me about any of that, I'm more than happy to do that. That's my perspective and why I've done those things the way I have. But again, if you want more practice, make sure you do check your understandings first. Check your answers against my answers. And then if you got it right, you probably know what you're doing. If you got it wrong, then that's when you may need to ask a question. Or when you're doing check your understanding, you're saying, I don't know if this is fully enough to show clear evidence or clear, consistent, convincing evidence. That's a great time at the beginning of class to ask that question, right? When I give you a chance to ask questions. Does that make sense? Okay. Please hear me very clearly. I'm not saying no to those suggestions, but that's my perspective. I'll be more than happy to talk about it further if you want to at some time. All right, let's get started with today. Let's look at that bell ringer first. So, come on computer, I know I haven't restarted you in a hot minute. That's not bad. Okay, so first things first, which mathematical representation is shown to the left? So what are the 5 mathematical representations? Graphs, tables, pictures, verbal, your words, and then algebraic, right? Your algebra, your equations, things like that. Be careful, right? So I see slope and exponential. So let's look at this really quickly because this is important. So when I look at this graph right here, does it have a slope? Slope only goes for one type of function. Well, y equals mx plus b has slope involved, right? Where's the slope in that equation? M, right? So be careful, right? Slope, because this is a slope-intercept form of a line. However, what type of function is that? Say again. So that's a representation. What type of function? Like if I were to graph this, what would it look like? It would be a linear function, right? And so we need to keep in mind function versus representation, and so we need to be clear on that language. And so I'll work on being more clear about that moving forward. But we're going to talk some today about relations versus functions. But go ahead and start training yourself to think representation, tables, graphs, equations, well, your algebra, words, and pictures versus the types of functions. Linear. One person did correctly identify this type of function, though. What was it? Someone said it. Someone put a type of function. This was an exponential. Hopefully you remember that from Ms. Williams' class or whoever we had for Algebra 1. Regardless, we're going to talk about it some more because we need to know why it's exponential. So that's what the later part of today is all about, is learning what do we mean by exponential and why is that exponential. But we're going to contrast linear and exponential functions. So mathematical representation, though, keep in mind tables versus graphs. After that one, so yeah, what do you know about f of x equals 3x minus 5? So we have a downward slope, we have a positive slope. I know when your calculator put it on a graph, it would give you the answer, positive slope. Okay, so let's talk about this. It's algebraic slope form. Okay, right here, it's what? Anyone see what that says at the bottom? It's linear. So, all right, we got a lot going on here. So let's do this. How can I check to see which of these things are correct? Okay, we got technology, right? So what can I do? Make a graph? Okay. Now, please pay attention to this. I designed this question to help prepare you for what we're about to do, right? This isn't for kicks and giggles. This is to help us prepare. So, documents, I'm going to make, and I'm just going to make one. Don't sweat about making your own at this point. All right, so I'm going to type in 3x minus 5. Okay. So what features do we notice? Nope, that's not what I wanted. What features do we notice about this function right away? Positive what? Positive slope? Okay. Let's not forget the most important thing, like what kind of function is this? It's what? Is this one exponential? I would say, what shape is that graph? That shape is a line, so it is linear. Okay, cool. It's linear, right? It's got a positive slope. Does anyone know what the slope is or how I could find it? Say again. Say loud. 1 over 3, so 1/3. How do we calculate slope? Now I'm going to go ahead and tell you, this is great if you're talking about looking at it graphically. What I'm going to recommend and always use is, I'm sure you've seen this before and how to calculate it from 2 points. Have we seen that? I hate this. It makes it so much more complicated than it has to be. Hopefully in your science classes, especially if you're already a junior, if you're a sophomore you may not have seen this, but there's an easier way to write this. That's just how much it's changing, right? Like if I'm going from 5 to 8, how much did it change? 3, right? 8 minus 5 is 3. So this is not a triangle, this is the Greek letter delta, and that Greek letter delta in math and science just means change. So what am I saying? It's the change in y. That's how much the y is changing. Divided by, the run is going to be the change in x. So change in y, change in x. That way, when we start looking at things like this, so now when I look here, change in y, how much is it, what's happening to go from 7 to negative 2? What's happening to the x? None. I don't have to fool with the minuses, I don't have to fool with all of the, like, making sure the signs change. It's just, how much is the y changing, how much is the x changing? That's it. Okay? That's going to be my recommendation. If that's like, ooh, Mr. Kinney, that's new. Yeah, it's okay. New just means something new to learn. It'll take time, and that's okay. But that's what I'm going to do with it. But what I would focus on is, remember, go to the graph. Oh, the reason why I say this is easier if you don't have a graph. And it always works for a graph. So if I go to this point, how much is the y changing? 3. How much is the x changing? 1. So notice, very, very close, Kelly. I loved that you recognized the 3 and the 1, but see how it's the reciprocal, right? Which makes sense. Look at that equation. Why is it 3 divided by 1 based on that equation? Look at the equation. Why is it 3 divided by 1? No, look at the equation. Why should it make sense that my slope is 3 divided by 1? Guys, do you see 3 divided by 1 anywhere in that equation? You don't see it?
Yeah.
Where?
3x.
Okay, 3 is the same thing as 3 divided by 1, isn't it? When you say 3 divided by 1, you get 3. Okay, so 3x. Right? That's slope, intercept form. Okay? Now it's going to come up, the reason why I'm really emphasizing this, by the way, what is this b again? That's the what? The y-intercept. If I look at the y-axis, -1, -2, -3, -4. Do we see a y-intercept in -5? Okay, so some of us noticed that negative and talked about a downward slope, right? But a negative doesn't necessarily mean a downward slope because that's my y-intercept. Don't forget, y-intercept and slope. Okay? Now, this is really why I'm asking this question, because this is kind of what I was wondering if we recognized or not. Remember, there's 5 different representations. We've already looked at it graphically, correct? Already talking about it, connecting it to the algebra. I want us to look at this table really quickly. So 0, -5. The next clear point I can see is 1, -2. The next clear point is 2, 1. And the next clear point is 3, 4. Anybody know what the next clear point should be? See anything happening there? How'd you get 4, 7? When you say going by 3, what do you really mean? See that plus 3? And then this is plus what? Oh my goodness, it's like that 3 divided by 1, because it's the change in y divided by the change in x. Notice it's harder to see rise and run there when we're looking at a table, but that change in y divided by change in x always works. Okay? Now, The reason why I do want to, I'm really emphasizing this, and I want to bring this up before you go into the task that we're about to do is this. Mathematically, how do we show repeated addition? Wait, it's multiplication? And what's happening between this 3 and this x? They're being multiplied. This equation is not random. It's not that someone just made it up for kicks and giggles. The reason why this equation exists is because, what type of function was this again? It was linear, right? And a linear function has what type of rate of change? Not just the same. I'm going to write constant here because it is the same, but it's constantly what? Adding. A linear function has a constant additive rate of change. And Brianna, how do we mathematically show repeated addition? And so my rate of change is multiplied by my variable. That's why that's happening. I do want to give you a couple of minutes to, I would get out my Frere model with the mathematical representations, and I would make some notes in the notes section, not in one of the tasks, but in the notes section. I would make some notes about this idea of linear functions, right? This is going to be the backdrop to understanding, well, that is the foundation for understanding linear functions, and that is also going to be the key to understanding exponential functions that we study a little bit later. So, write down what notes you need to. If you need to write down this note about slope here, right? This alternate way to see slope, please do that. I always use that instead of the y2 minus y1 divided by x2 minus x1. If you want to write down the table and show that +3 and that +1 and connect it to that equation, that's a good idea. But definitely make sure you understand and have a note that the slope is a constant additive rate of change. And so it is multiplied by x, because multiplication is repeated addition. That is fundamental to understanding everything in linear. Everything in linear. If you want to make your life easier, you can turn the desk. Guys, if you're ever in a desk that's got your back to the board that I wrote on, please feel free to turn your desk. Trying to raise money funds, that's the thing I was trying to say. The funds right now, I'm getting new desks that move more easily, but just haven't happened yet. It costs money to buy stuff. You know, we don't have a lot of in education. We don't have a lot of money. Especially since we shut down the attempt to get higher taxes. Do you know the state of Alabama has like the second or third lowest property taxes in the entire country? You know we also have the second or third worst education in the entire country? It's like there's a weird correlation there. You know who have the best education systems? The ones with the highest property taxes. I don't think that's necessarily right, but man, if we only charge a little bit more and had more resources for our students. Or maybe if we got a lottery, that helps, you know, Florida and Georgia a lot.
Yeah.
Huh? Up north, yeah. There's a lot of issues up there too, but
They do have more.
they do, the kids do, 100%.
And also the best universities are up there.
So again, don't forget, make sure you understand that idea of slope being the constant additive rate of change. And it's multiplied by x because multiplication is repeated addition. I'll try to, you can have everything printed out that we're going to use or today before you leave. Don't let me forget at least.
Oh my God.
I know a couple of us are still taking notes, so I'm going to give us about 60 more seconds, but I'll leave that up there. But I do need to start talking about a few other things. Alright, one thing I want to emphasize and point out here is this. Does anyone remember what I mentioned about the power of a table, like why a table would be really, really good?
It's good for organization.
It's great for organization, right? It helps me stay organized. What's the next piece of it? It helps us find patterns. What type of relationship, what type of function could we use to represent what Roy and Joel were doing? Or with their cost of going to the pool? Not sure? Alright, kind of tell me this. What's happening every time for Roy? What's happening to his cost? It's adding by 25? Wait, you're constantly adding by 25 every time? Let me ask y'all again, what kind of function could represent the cost for Roy going to the pool? Say it louder.
Linear.
Linear. Ah. What about for Joel? What's happening to Joel every time? It's adding by 10 every single time. Because that is constant additive, we should be thinking about what type of functions. What type? Linear. Now, if I come up here, I have this equation. Roy, the amount of money he spent, is 25V. Why 25V? Where is that coming from? Okay, the V is the number of visits, but why 25V? Because it's what?
How much money you spend each day?
So, 25 and V is how much he spent each day? No, which part is how much he spent each to visit?
25.
He spent 25 each visit. V is the number of visits, so why is it 25V? Okay, so we don't know how many times he visited, but why is it 25V? Why 25 times the number of visits? Okay, let me emphasize something. Miles was close to a detail that we're forgetting to include. Why is it 25 times? Like 25V is 25 times V. Why is it times? What's happening here? Repeated what? Addition. It's constantly adding by 25. When you see constant additive, you should be thinking about multiplication. But there's nothing after it or before it. But with Joel, I assume this was supposed to be 240. With Joel, it was 240 plus 10v. Why 240 plus 10v? I don't see a 240 here. Because what? Because he paid how much up front? Okay, so please notice, it's a good idea to start with what input? 0, especially if you're dealing with linear exponential. An input of 0 is a great time. Because notice, Roy spent how much if he went 0 times? 0. But in contrast to what we say over in group 1, the aces over there, how much did Joel spend if he went 0 times? He still had to pay that fee. Now, why would he pay that fee if he went 0 times? I don't know. But he had to spend 240, which is why, what's right here? How many times did he pay that 240? Once. So am I multiplying anything here? No. It's 1 time of 240 plus 10. What's happening between 10 and v? They are being multiplied. Right? And so there we go. That's 240 plus 10v. And so now we have explained this, right? By the way, this is also plus 0. And once we recognize our two equations, I think someone up front said this while we were there setting up. They said, hey, can we just set them equal to each other? Well, this is how much money Roy spent. This is how much money Joel spent. And we know they are the same. 25v equals 240 plus 10v. Right? So we have a couple of groups who did that yesterday right here. One thing I want to emphasize is don't just write minus 10v. I talked about this yesterday. What are you doing? You are creating a 0. Remember, that's what had to happen first, right? We subtract 10v first here to make it 0. And then, why am I doing it over here as well?
What you do on one side, you have to do.
What you do to one side, you have to do to the other. That was called a property of equality, right? That's the idea. Because even though, like, does this equation and this equation look exactly the same? I got 25v here. I don't have a 25v, do I? No? Does this look exactly the same as either of those? But are they telling the same story? Yes. No matter which of these equations I look at, what is v equal to? 16. That's the idea of properties of equality, right? I have to make a 0, I have to make a 1 so I can get v on its own. But what I do to one side of the equation, I have to do to the other, so that even though they look different, they're telling the same story. Looking different, but telling the same story, that's the idea of equivalence. You're going to hear me talk about equivalent functions a lot. So just go ahead and start lodging that in the back of your brain. They look different, but they tell the same story, so they are equivalent. Look different, but tell the same story. So they're what, Kyron? Equivalent. Okay? And so 16 times. One of the last details I want to point out here before moving on is this. I love this right here. Why? Because what? Not just, well, so the justification is all of this, right? This is justification. This is evidence. When we say justification, it's evidence for how we got this. But what does this have? Context. Guys, I know we're used to just dealing with random equations, but notice y'all used M and V for money and visits because we're not dealing with random equations, we're dealing with the real world. When you have a real world context, ending it with context is a good idea. And by the way, we all saw the table, right? All of us carry the table out to $400, 16 days, or 16 visits, I think. Does this tell the same story? Yeah? Was the table too bad in this situation? No? But what if it had taken 50 visits to get to the same amount? Would that have been rough? So this is why we want multiple representations. Because I don't want to carry a table out to 50 or 100 or anything like that. But if I can get an equation, does that make things way easier once I have the equation? 100%, right? That equation can make things way easier. By the way, could you have used a table and stopped, and I apologize for erasing y'all's work, but I just want to point this out. Could I have stopped my table here if I saw the pattern and realized how to make that equation? If you can start a table to help you find a pattern to write an equation, can you stop there? 100%. And then I can't see a whole lot here, but let's go to Windows/Zoom. Again, I'll help support you in developing this. But we know it's 20 or 16 visits, so I'm going to make my X max 20. I know it was $400, so I'm going to make it go up to 500. What do we see in this graph that could have been real helpful? That point of intersection? Any guesses what that point of intersection might be? 16 comma 16 comma what? Oh yeah, 16 visits, they spent $400. So I want to emphasize and I want to point this out because I want y'all to see this. Tables are great for organizing and finding patterns, which that organization, those patterns can help you find an equation. Graphs are really helpful for finding points of intersection and where things overlap. Okay? And equations can make it easier to do algebra. But they all are interrelated. Did any of those representations tell a different story? Every single way we looked at it, 16 visits for $400. That's another thing where, man, the table, the graph, the equation, they all look different, don't they? But are they? So what would we call them? They look different, but they're telling the same story. Say what? They're equivalent, right? These are equivalent functions. Different representations, but exactly the same function all the way through. So they are what? Equivalent, right? Be looking for that equivalence. That's the beauty and the power of tables, graphs, and equations. They can look radically different, but they're telling the same story. And so what we're going to do this year in mathematics is we're going to try to find a story. What's the story being told? Because there's beauty in that. All right. You ready for a new one? Talked about this one long enough? Yeah? All right. I will pause a second if you, actually, yeah, let's do that. Let's pause a second. If you want to take notes for the swimming pool, you can definitely do that. Remember, I did give you that prayer model. That was specifically for the swimming pool option. Okay? So if you want to take notes about the swimming pool, remember, this is not content I'm going to test you on, so don't just write down the steps. Write down the major ideas, like making a note of, man, the table and the graph and the equation were telling different story, or looked different, but they're telling the same story, so they're equivalent. That's powerful. That's useful. Noting in the Roy and Joel that, hey, it's adding the same amount and showing that connection to the equation, that's powerful, right? Understanding why. So that's one thing to remember is notes should not just be the pure thing, but the reason behind it. Because if you don't understand the reason behind it, it's hard to internalize. So try to understand that thing behind it. Sorry, I totally forgot to check that. What number?
3.
Thank you. Who's 16? Thank you. Let me make it warmer. And by the way, if you want to, I just thought about this, if you want to write down a quick note about the context here, that might make these notes make more sense, just so that you're not like looking at the table and the graph or the equation, you're like, where the frick did this come from? The context of that problem might be helpful. So, right, we have the seasonal pass of 240 with $10 for each entry fee, $25 ticket for each entry. And they spent the same amount. Okay, you can get it? Okay.
Stop.
So we will move in a second, but hold off on moving. Hey, really quickly, I meant to mention this because I heard some students in here talking about this yesterday. They're like, why in the world would you pay $240? Please note here, before 16 visits, which option should you go with? Which one was this blue? The $25 every visit, right? But if you go more than 16 times, which option should you go with? The 240 first, right? So this is where we need to think through different plans and offers being made, because you have to think about, am I going to go short term or am I going to go long term? Am I going to go less than 16 times or am I going to go more than 16 times? Because that should inform which route you go with. So this is why we want to be developing our mathematical sense so that we can analyze 2, 3, 4 different options and find the best one for what works for us. Because I can tell you this, we bought a car just a few years ago and there were options of, hey, do you want to get a car protection plan that covers the physical components of the car, like the interior and the exterior? Do you want to get one that covers the, what was it, like certain parts of the engine? Do you want to get an oil package? And we had to analyze the situation and say, okay, what's going to be better for us long-term versus short-term? And so make data-informed decisions.
You got the oil package?
No. No. Did we get the oil package? Yes.
I did get the oil.
Yes. Because the cars that we got were Subarus, and so like they have to use some specific synthetic oil, and so it's going to be cheaper to just go to the dealer. At least with that option. Good. All right. So normally I like to just tell a story to get you there, but I haven't used this problem 3 very much, but it is a really good one, and I want to wrap up with all this. So at Old McDonald's farm, there are chickens and there are cows at the farm. All together, there are 70 heads and 186 feet. How many chickens and how many cows are there on the farm? So on Old McDonald's farm, there are 70 heads and 186 feet for the chicken and for the cows. How many chickens and how many cows are there? Let's get up, let's go to our groups, let's start talking. Make sure you get to know the people inside your group, and let's figure out how many chickens and how many cows there are. Miles like looked excited, he's like, oh, chickens and cows. I'm in. That's the context I've been waiting for, Mr. Kenny. Dang, Brianna's impatient.
Wow, it really is.
So, I just want to point this out. First things first. One of the things that a lot of us missed at first, but some of us got right away, is the equations, and I totally get it, right? When I see, though, that the cows and chickens all together, what key operation should I think about? Addition, right? When we're talking about things all together, we're talking about addition. By the way, I also like how some of us started to realize and think about different variables, right? Cows, we use C. We can use C again. So we used H. Was that for hens, I'm guessing? Mm-hmm. Yeah. This group over here did P, which they used some other word that I wasn't thinking about, but I thought immediately of pollo, which is Spanish for chicken, which is where, I'm sure it's a Latin word that your term came from. But we have these variables now. We have these equations, and all together, each cow has how many heads? 1, so it's 1C. Each chicken has how many heads?
4.
So it's 1H. Add them together, 70. So we cannot forget this, and this would have helped us get to the equations a lot faster. How many legs does or how many feet does every cow have?
4.
So every extra cow, what's happening to the number of feet?
It's
It's being added by,
4.
oh, and because we have repeated addition, we have multiplication, right? It's 4C because every cow adds 4 more feet. Every chicken adds how many more feet? So it's 2 times H, and all together, so they're being added, it's 186. Now we got our equations, and did some of us try to make a table here? Did it get ugly? Yes. Please hear me clearly. I let you struggle with it. I know you're not going to like me for it. I let you struggle with it though because I need you to understand tables are not always the best. They can be really helpful. But if you catch yourself realizing, frick, I have no clue what's going on, stop and try something else. Okay? If you catch yourself going, man, this is not working out, it's okay to stop and start over. Why do you think you're at a vertical surface that you can easily erase on? Because math is messy and we make mistakes. So stop and start over. A great option that some of us got to was a graph. Graphs are really awesome for looking at systems and things like that. And I know, I think it was Drake was like, but I don't know how to use this calculator. Well, guess what? I do. I'll teach it to you. Just ask those questions and I'll be more than happy. If you're like, Mr. Kinney, I want to do blank, but I don't know how to. I'll show you. That's my job as a teacher, okay? So, what lets me do cool crap, by the way?
Menu.
Menu, oh, that's right. Now, remember, in order to, and then if I want to create a graph, graph entry / edit. Now, if I want to do function, when you pull function up, what it's going to say is f1 of x, or f of x. That means I need y equals in order to type that equation in. Do we have that right now? Now, by the way, could I have made it that way?
Yes.
Could have, and could have done function. But it's easier on these calculators. Just type in relation. X plus y is equal to 70. Hit enter. Oh, no, there's nothing there. It's okay. First off, I'm going to put my second equation in. 4x. Now, in this case, remember, note 186. Don't freak out when you don't see anything there. Pause for a second and say, hey, do I just need to change my window? Because how many cows could I have? How many chickens could I have based on the number of heads? 70 of each, right? 70 of one, 0 of the other. So I'm going to go to Windows/Zoom, and Windows settings gives me more control. And we just said that the maximum number was 70. The maximum number was 70. Now do I see something useful? And if some of you are going, but Mr. Kinney, mine didn't look exactly like that, that's okay, because that probably means we just flipped the chicken and the cows, but it's going to give us the same exact answer. Analyze that graph, point of intersection, and I did cows first, and then chickens. 23 cows, 47 chickens, is that what we got?
Yeah.
Right? More than one way to do this. Now, I do want to quickly talk about this algebraically because this is going to be helpful for us long term. So C plus H equals 70. 4C plus 2H is equal to 186. One method that you can do here is substitution. That's what this group talked about. But remember, if substitution, I have to have one variable equal to everything else to be able to substitute it in. So how did I get C equals 70 minus H? I didn't have to do anything complicated. I just used inverses in that equation. I wanted to know what C was, so I don't want H, so I subtract H. C is equal to 70 minus H. Now, what can this 70 minus H be substituted in for? What is that 70 minus H equal to? Number of cows, right? So what can 70 minus H be substituted in for? Number of cows. Woo! 4 times 70 minus H. And yes, I'm going to have to move a little quicker. But that's 280 minus 4H plus 2H equals 186. minus 280. Because what am I making here? Notice how I did that on the left-hand side, because I'm making a 0 first, and then whatever I do to one side, I have to do to the other. I can go ahead and simplify this. I'm taking away 4 h's, and I'm adding 2 h's back, so I have negative 2 h's. Negative 94. I use that reciprocal, 1 divided by negative 2. Anybody want to take a shot in the dark what negative 94 divided by negative 2 might be? How about that 47 we found earlier? Didn't we find 47 earlier for the number of chickens?
Yeah.
Yeah? Okay. Now, that was substitution. You substitute that back in to get the number of cows. But honestly, guys, when you have what's called the standard form of a linear equation, it's easier to use elimination. There's a couple different ways I could eliminate here. But what would eliminate a positive 2h? A negative 2h. Oh, so if I multiply this thing by negative 2, I get negative 2c minus 2h equals negative 140. 4c plus 2h equals 186. And when I add those two equations together, what's negative 2h plus 2h? Oh, so I've eliminated my number of chickens. Negative 2c plus 4c is 2c. 2 cows is equal to 46. Take half of that. Let's create a 1. Number of cows is equal to what? That's a little familiar. So, this is elimination, this is substitution. I apologize for going a little long. If you want to grab your phone and take a picture right now, you can, but then I do want you to start doing notes to your future forgetful selves. The primary purpose of this is to learn how to think flexibly with mathematical representations. So, is it okay if you start with one representation and have to switch? Yes, I do that regularly. They tell the same story, but sometimes one is easier than the other, right? So, think flexibly. That's not something I have written on the board, but it's something you got to know. The whole point of this is think flexibly, but also hopefully a review about solving and things like that.
Is this recording? I hope not.
Yes, it is recording.
Jesus. And I'm all in it.
Using the Lord's name in vain.
My
on
bad.
recording. Dang. Dang. Okay.